Hi everyone. In this video, I'm going to go through a trace of how linear search works. So linear search is a searching algorithm that walks through and checks each item, trying to see is it the value we're searching for. So one thing that's kind of nice about linear search versus, say, binary search is the array doesn't need to be sorted. But linear search is not as efficient as binary search because the array doesn't need to be sorted. That's what binary search takes advantage of to be a little bit faster than linear search. All right, so I've got 9 random playing cards here in a random order, and I've got the indexes for each card above the card. So 7 is at index position 0, 4 is at index position 1, etc., all the way up to 5, which is in our last valid index position for a 9-element array of cards, which is 8. So the green bar down here, this is kind of representing what portion of the array is still needed to be searched. Okay, so initially, we haven't started linear search yet. The whole array needs to be searched in order to try and find a target value. The target value we're going to look for this first iteration is 8. So you can see 8 is in the array. It's right here at index position 4. Let's trace through the algorithm and see how linear search finds 8. I've included a function here that implements a linear search algorithm. You can take a look at it if you want in order to check in and see where we are in the trace and where we are in the code. All right, so I'll put that back down over there in the corner. All right, so how this algorithm works is we have this index, which I'll just call I. You can see its index in the code, which starts at the first valid index in the array, which is 0, and increments by 1 until it goes through the entire array. If we find the value we're searching for early, then of course we can stop checking because that would be inefficient to keep checking once we've already found the value we're searching for. All right, so let's say we're looking for 8. So the algorithm starts at I, which is 0, and asks, is the value at I equal to our target value? Is 7 equal to 8? No, it is not. So I increment I to prepare for my next iteration of the loop, which shrinks the portion of the array we haven't searched yet by 1. All right, next iteration, we ask, is the value at index I equal to the value we're searching for? Is 4 equal to 8? It is not. So we increment I to prepare for our next iteration of our loop, which shrinks the portion that we haven't searched in our array down by 1. Next iteration, which is our third iteration, we ask, is the value at I equal to the value we're searching for? Is 3 equal to 8? It is not. So we increment I, which shrinks down our portion that we haven't searched yet in the array by 1. Next iteration, fourth iteration, we ask, is the value at index position I, which is 10, equal to the value we're searching for, which is 8? No, it is not. So we increment I to prepare for our next iteration of our loop, which shrinks the portion of the array that we haven't searched through yet down by 1. Okay, now we're in the fifth iteration of our loop. We ask, is the value at I is 8 equal to the target value we're searching for, which is also 8? Yes, it is. So we have a match, right? We found the value we're looking for. So what we do is we make a note of the position which we found it at, which is I. We stop searching and we return that position I, which is 4. Okay, so the code here sets a flag variable found to true, records the index I at which we found the value position. Okay, so if you look at our Boolean condition here, it's a compound condition and not found. When we set found to true, not true is false. We break out of this loop and we return the position at which we found our item, which in this case is position 4. All right, let's go through and do another trace of the algorithm. Let's say the value we're looking for is 7, right? This is the best case scenario. The first element we check is the value we're looking for. So starting over, I is 0. Okay, we ask, is the value at index position I, 0, equal to the target value? 7 equals 7. Yes, it is. Great. We return index position 0. All right, that was a quick one. All right, let's do another example. Let's say we're searching for 11. okay? So 11 is not actually in this array. So let's go through the entire algorithm and see what happens when we don't find our target value. All right, I is 0. Is the element at index position I equal to our target value, 7 equal to 11? Nope. So we increment I. Next iteration, we ask, is the value at index position I at 1 equal to our target value, 4 equal to 11? No, it is not, so we increment I. Is value at index position 2 equal to 11, 3 equal to 11? Nope, so we increment I, shrinking our portion of the unsearched portion of the list. Is the value at index position I 3 equal to 11, 10 equal to 11? Nope. So we increment I, shrinking our portion of unsearched list. Is the value at next position 4 equal to 11? Is 8 equal to 11? Nope. So we shrink and we shrink. And I think you can see what's going to keep happening here. 6 equal to 11? Nope. So we shrink, increment I. Is 9 equal to 11? Nope. Shrink, increment I. Is 2 equal to 11? Nope. Shrink by incrementing I. Is 5 equal to 11? Nope. So we increment I. I is now 9, okay, and there's nothing else to search, okay? So if I is 9, index is 9, and there are 9 elements in our array, 9 less than 9 is false. We break out of this loop. We return position. Position was initially assigned -1, and since we never updated it, we return -1, which is kind of a dummy value for representing we failed, right? We didn't actually find our target value in the array, so we return -1, which is not a valid index. So the calling code needs to check our return value from this search list or this linear search function to make sure it's not -1 before it uses the return index, because if we fail, we're not going to return a valid index. All right, so that's linear search. Thanks for watching the video. Also check out my video on binary search so that you can see a more efficient searching algorithm.